So we've got 3 computers on this morning. Okay, well, welcome back. Presumably we've been talking about vectors, and the problem is we lose 2 days. It's going to hurt us because we were already short 2 weeks this semester because of COVID. And so I'm not going to be able to do everything that I wanted to do. I'm a couple of days even shorter than I hoped. So I want to get to stuff. One of the things that I'm going to put up on the screen, sorry, I've got to make myself a co-host, which I thought I was. One more person coming, that's good. So where is, why am I not, there I am, okay. Make myself a co-host, which was already done, but it failed. So now I'm a co-host, now I can share the screen. I say that. Why is it not? It's got Natalie Kosterman as a co-host. Apologize, Natalie, you are now a co-host. I suppose you can get rid of all of us. It didn't make me a co-host, it made Natalie a co-host. So I'm going to go up and wherever. Sorry for this extra time it's on this. I don't want to waste any more time. I'm taking Natalie's co-host permission away. So you lost out, Natalie. You didn't get a chance to change all our grades and stuff. Okay, maybe we can share the screen. Maybe not. It's third time I've made myself, or fourth time I've made myself a co-host. Now I'm a co-host, yay, yay, yay. So you're going to be able to see these wonderful notes that you've had in your possession for a couple of weeks. Okay, so assuming that you can see these notes, and by the way, if anybody else knocks on the door and you can see that in any way that they're missing, please let me know, because when I'm looking at all this, I don't see that. So I'm going to look at over here at the screen myself. What I'm putting up here is I want to emphasize this norm or direction. We're going to go through, this you've all seen, I hope, but in the notes is like page 35. I define the norm of a vector, and you'll notice up here it's the dot product of a vector with itself. And I put 2 lines around it. In the text, they only use 1 line, but that's will confuse you with absolute value. And I like to use a bold print for vectors. I put a line under it if I'm doing it on a blackboard or on paper. And it means the length of the vector. It's the square root of the sum of squares of the components. And if you have n components, like 50 components, it'll be the sum of 50 squares. And anyway, I've got a message about Flash Player on my screen. That's what stopped me. Adobe is like Zoom, it's pernicious. Okay, so we've talked about this many times already, but if somebody says, what's the direction of a vector? You multiply the vector by 1 over its norm, that's a scalar. You do that by putting that number into every component. Okay, now, what the book doesn't emphasize, mentions certain times, but doesn't emphasize, the properties of this norm. One, if I have a scalar multiple of a vector and I want to take the scalar out of the length, in other words, the length of alpha u, what is that? That turns out to be the absolute value of alpha times the length of u. So what multiplying by a scalar does is it changes the length of the original vector. If alpha is bigger than 1, it's going to make the original vector bigger. If alpha is less than 1, it's going to make it smaller. And if alpha is negative, it's going to turn the vector around, but it's not going to change what its length would be. So that's why we have absolute value. Secondly, you already know about the cosine of the angle being the product of the norms times the dot product over the product of norms. Since the cosine is always less than or equal to 1, you get this inequality. It's called the Cauchy-Schwarz inequality. It's actually called nowadays the CBS inequality because there's also a Soviet named Bunvyukovsky, and I've got somebody wanting to come in. We've also got a Russian named Bunvyukovsky who also worked on this back a couple hundred or 150 years ago. So we have the Cauchy-Bunvyukovsky-Schwarz inequality, trying to give everybody equal rights. And so it's sometimes called CBS inequality, but usually called Cauchy-Schwarz. I didn't mean to move that. And that's just saying the absolute value of the number, which is a dot product, is less than or equal to the product of its norms. Okay, now, when is the absolute value equal? And it's equal if and only if one of the vectors is a multiple of the other. So you only get equality in the absolute value of the dot product and the product of norms when one is a scalar multiple of the other. The fundamental representatives of vectors come out of the origin. It just says they lie on the same line through the origin once we get to talking more about lines. Now, important one here is called the triangle inequality. We will use this a lot in Calc 3 mostly, but we'll use it a lot. Now, key, and one of the reasons I wanted to talk about it is how would you prove something like the triangle inequality? Now, all the proofs are down here, down the page, but the one I want to look at is number 4, because I want to try to show you the way you can do some things sometimes. If I'm trying to prove something with norm, you can't do much with it. So what we do is we square it, because this is just a number. So you multiply it by itself. And remember what the definition of a norm is. It's a dot product, the square root of a dot product. So if I square the norm, I get the dot product. And we have properties of dot product, namely we can distribute. And so I'm distributing the u over the u plus v here. And then I distribute the again, and I get 4 things here. Now, because dot product is commutative, that means these 2 things are equal. I can add these up and get 2 of them. And now when I look at it, I got a perfect square. Not quite, not yet, that's wrong. I thought I had a perfect square, but I don't. But if I now use the Cauchy-Schwarz inequality, I can replace this number by this number, the product here. And that's true whether it's negative or positive, because this dot product is less than or equal to the absolute value of the dot product, and that's less than or equal to this. So I can replace this sum of square thing with this one, which is bigger. And now I have a perfect square. If I have a square on both sides as a perfect square, I can take square roots. Now, if this is positive and I square it, and this is positive and I square it, when I take square roots, it will preserve the inequality. And so what you get from the squares is you get the original thing up here, which is this triangle inequality. So you ought to learn that proof, not because that proof itself is so important, but the techniques. There's 2 different techniques here. One is to show you how you use the Cauchy-Schwarz inequality sometimes, because this dot product is harder to work with now, and we can replace it with this norms. On the other hand, norms are sometimes hard to work, and we replace them with dot products. Okay, not the norms themselves, but the square of the norms. So this little proof is kind of a prototype for the kind of stuff we do when we're proving some of these things. And now, after that in these notes, I talk about distance. Distance is also in the text. In the text, the book, the author puts a box around the things he wants you to remember. I'm doing this without a box, but distance concepts. The distance from the vector v to the vector u, that's over here. Oh, but that's the same as the distance from u to v. In other words, distance is commutative. It doesn't matter when you're talking about distance between, it doesn't matter which one you list first. Distance is always greater than or equal to 0, and it's only equal to 0 if the things are the same. So if two vectors are equal, then the distance between them is 0. If two vectors have a distance between them is 0, remember how we think of vectors. They are not arrows, they're points in the plane. And if you want to think of arrows, you connect that point to the origin. But the name of the vector is the components that make up its head when its tail is at the origin. So 2 points are equal if and only if they're the same. And that's the same way with the distance between vectors. Distance satisfies what we call, again, the triangle inequality. The distance between two vectors is less than or equal to the distance between you and a third vector and the distance between the third vector and the second vector. This is similar to the triangle inequality up here that we just proved a minute ago. It's 2 pages up, but I don't want to make you dizzy. But it's the same idea. And this is important. This is where we get parallel. The distance between two vectors, if I add the same thing to the two vectors, the distance between the new two vectors is the same as the distance between the old two vectors. And that's where we get a parallelogram. Because when we add the same thing to two vectors, we're going to create a parallelogram. So there's proofs here. And the other thing to mention here is the book especially sets out 3 vectors that they identify. One's called I, one's called J, and one's called K. That's because people like to treat these things as if they're numbers. And as long as you're careful about the arithmetic, you have to know when you cannot treat them like numbers as well as when you can. We can add them like numbers, at least in terms of the vector u plus the vector v is the vector v plus the vector u. That's commutativity and so on. But we have to be careful. In higher dimensions, we use E instead of I, J, and K. And we say E1, E2, E3 because we might have 50 of these. And the trouble is that the English alphabet only has 26 characters. And so even if we use all 26 characters, we run out of characters. So it's mathematically, we'd rather use E sub 1, E sub 2 and stuff. Engineers prefer to use I, J, and K because engineers are generally dealing with 3 dimensions. Okay. So there's nothing wrong with I, J, and K except they get too familiar and then you make mistakes because you use them too much like numbers, and sometimes you shouldn't. Well, we got some other things here about distance and stuff that you should have read by now. And this is trying to set up things that the author doesn't do a very good job of setting up, which has to do with what straight lines are. I don't want to talk about that right now. We've done that in the past. And so to drop down a little bit, we do develop what are lines through the origin here in the notes, and that's just take a vector. If you want to connect that head to the origin, that makes an arrow. And if you multiply that arrow by numbers, you get different vectors. But if you look at them, they're all going to be on the same line. And this is defining the line. The line is all those vectors that are scalar multiples of each other. So if I have a vector v, the vector 2v, the vector 1/2 v, the vector minus v, turns out when you plot all those points, you will get points on a straight line. So this is the equation of a line. I use some notation here just because it gets a little bit more complicated. And what is done in the next few pages, if you think about what you know about lines, these little theorems here are trying to tell you stuff that you already believe in, but you maybe never tried to write down. So I'm not going to do all of them, but let's talk about one of them here. What does it mean to say C is a member of this thing? Well, this was a notation for the line that passes through 0 and A. So if I say C is on the line between 0 and A, or not between, and C is not 0, then it's also on the line between, then A is also on the line between 0 and C. So think about having a line with 3 points on it, 0 and 2 other points. What we're saying is, if I describe the line with 0 and 1 point, and the other points on the same line, I could describe it instead with 0 and the other point. So if A is on the line through 0 and C, then C is on the line between 0 and A. That's what theorem 4 says. What's theorem 5 say? Every non-zero point on the line has direction, which is plus or minus the direction of the A that you're using to describe the line. Now, the direction is not A. Remember, the direction is the point on the unit circle. So that would be 1 over the norm of A times A. That's the direction. And so that's when you prove it, you bring that in. What's number 6 say? It says if I take 2 points on the line through A, that if I take their difference over their norm, that turns out to be the direction plus or minus the direction of A. So what's that saying is I can take 2 points on a line and obtain from that the direction of the line. Any 2 points on the line in the plane, take their components and subtract them, take the norm of that, multiply those subtracted components times 1 over the norm, you'll have the direction. That's what number 6 says. Okay? And then I try to explain things. But exposition means I'm trying to explain. The last 3 theorems establish every directed line segment on the line 0 through 0A can be characterized by a direction that is plus or minus the common direction of every non-zero vector on the line. In other words, they all have a common direction. And so this is teaching us about lines as if we did not have anything before. Now, where is this kind of stuff valuable? Because we know what lines are, but computers don't. If I do this kind of stuff and put this into a computer, then I can teach the computer about straight lines. When I say teach, the computer doesn't learn anything, but I can have programming that then we as visitors to the computer can believe the computer knows about lines. And so what we're doing is putting in what makes up a line. And this is the not the geometric way, but the analytic way to talk about lines. And then I want a line through A and B. Now, here's what it looks like. A line through A and B, if I know the vector A and the vector B. Now, the vector A and the vector B actually have arrows to the origin. I'm not talking about arrows to the origin now. I'm talking about points in the plane. If I want a line through those 2 points, okay, what you do is you take the difference of the 2 points. This is going to tell us about a direction. And I take 1 point and add multiple scalar multiples to the direction, and that gives me all points on the line. This is called the parametric equation for the line. And it's very important because it allows us to use a real number to describe everything on the line. By taking different points t, we can describe every point on the line. So if I have something on a line, like a road, and I want to talk about t as time, if I'm going down the road, I can think of the road parametrically, and then I can describe motion on the line. So when you have lines in geometry, they're static. You don't move around on them. You either have a line or you don't. When you represent a line parametrically using vectors, you can then talk about motion on a line. And we'll later be able to talk about motion on a curve, like we'll talk about flow on a river. So if you put a bottle in a river and you watch where it went, and if the bottle had some kind of dye marker, you could actually get a curve on the river that shows you where the bottle goes in time. And so we will later represent curves parametrically to be able to study motion. And it's important to have a one variable description, because with one variable, we can take derivatives. And it turns out that if I have a curve described parametrically, the derivative will tell me the speed that we're traveling on the curve and the direction. So that's all beyond what we're doing now, but that's one reason to be careful about how we define all that stuff. And that's why we have all these pages, and we have parallel here on page 41. And here I talk again about a line. This is just another way to write it. If you're given the direction first, not the 2 points, and you want to go through a point in a certain direction, this is the equation of a line. We'll get more to it. This is in section 5. We'll come back to that in a little bit. So I want to leave this now, except one more thing, and that is, what is a vector space? I don't know how much you want to maybe stare at this while I do this, but someplace here, sorry. Okay. A vector space. What is it? Well, I use all those kind of complicated math words. A vector space has two operations, addition and scalar multiplication. That's what that's about. And you know that now. What are the properties of addition? Well, the properties of addition makes the set of things an abelian group. Now, what does that mean? That means the addition is commutative, associative, there's an identity, and there's inverses. Okay? Now, that is, well, I'll get to it in a second, but that's spelled out in the book, and I'll show you in a minute. And then we have scalar multiplication. And what can you do with scalar multiplication? You can multiply a scalar times the sum of vectors, and you can multiply it all the way through. And so this is a sort of abstract thing that describes what a vector space is. All right, well, I want to get away from that. And now you see my ugly face again. And I want to go to somewhere else here. Okay, now we should see an attempt at a page of the book. And what I want to do here is go back a couple of pages here to where we talked about vectors in the book, and one more page or two back. Get there in a second. Sorry, the page. Here we go. In the book, I hope you can see this boxed in thing. It's on page 842 if you have your books there. Properties of vectors. Now, if the idea of you guys trying to understand what an abelian group under addition is and so on is a little bit abstract for you, the author summarizes exactly the same thing on page 842. Number 1 says addition is commutative. Number 2 says addition is associative. Number 3 says when I add a certain vector to another vector, I get it back again. That's called the identity. And with what we do in our plane, that's a zero vector. Number 4 is every vector has an inverse. Number 5 is where you are taking C times A plus B is CA plus CB. You see how easy it looks there, how more complicated it looked when I have my notes on the screen, but it's the same thing. These are the same properties that I listed. Now, I just got a message that says my internet connection is unstable. Has anybody had any trouble seeing what's on the screen and stuff?
No.
I don't know why I get a message saying it's unstable, but with the weather, you guys, and the way things happen Monday and Tuesday, if I lose you, I will try to get you back, okay? Anyway, I don't know why I got that message, but if anybody had any interruption of power or something from me, I'd like to know it sometime. I don't know why. I've got very powerful computers, but the internet connection is bad. So I'm looking at my router and my modem. They look okay right now. Sorry for the interruption. Okay. So anyway, in the book, he doesn't have all these mathematical words like I did, like group and stuff, but he summarizes properties of vectors. Now, he is talking about arrows. Remember, that's what we're talking about. But I want to do something else. And for this, you're going to have to just think a little bit. I want to talk about something called a matrix or an array. Now, I presume you may have had those. Has anybody, let's say, never heard of a matrix and array? Any of you? And don't feel bashful. I need to know that because it depends on how quick we talk about it. Have you all, has anybody never heard of an array or a matrix? I didn't say you could pass a test on it. I just asked if you've heard about them. If you're used to computers, sometimes we call that a spreadsheet. Namely, what we have is a device of some sort in which we have rows and columns that we can make entries. And so if I make myself up something that has 3 rows and 2 columns, like a spreadsheet, we call that a 3x2 array in math, or a 3x2 matrix, because we usually put numbers in it, not words and stuff, although we could. But a matrix is something with rows and columns. And for us, it's going to be numbers. Now, if you write a vector horizontally, you can think of it as a 1 by however many components you have matrix. Except when we write a matrix down that has 1 row, we don't write commas between the entries. When you think of that 1 row thing, like let's just take the pair 1, 2. If I wrote down 1 and 2 next to each other, not 12 now, but 1 and 2, like you think of it as having 1 in one box and 2 in another box, we can make a row of 2 columns. I put 1 in the first column and 2 in the second column. If I did that, that makes a matrix, and it's called a 1 by 2 matrix. We list the row first and the column second. If I put commas between 1 and 2, that makes an ordered pair. When we have ordered pairs, we normally put parentheses around them because we don't have a box, like a matrix box. So vectors can be thought of as a bunch of rows of a matrix. Or they could be thought of as a bunch of columns of a matrix, because I could write 1 and 2 vertically instead of horizontally. If I did that, I'd have a 2 by 1. So I can think of the pair 1, 2 as 1 comma 2 with parentheses around it. I can think of it as a vector, a point in the plane with angle brackets around it. Or I could think of it as just 2 numbers, and I'm going to put 1 in one box and the other in the other box. The boxes could be horizontal or vertical. When I think about this as boxes, I'm thinking about matrices. Now, if I would take something, let's take something with 3 rows and 5 columns. 3 rows and 5 columns. I hope you can envision that. If I took a second one with 3 rows and 5 columns and added each row and each column together, depending on where they are, that would be like adding vectors. So if you think of, for a minute, a 3 by 5 matrix as 3 vectors written vertically, written horizontally, but it makes 3 vectors. And if you added all that, you would add all the first components, all the second and the third. What I'm hoping you see is if I add the 2 things together in each row and column, that's like adding vectors. So if I have a 3x5 system and I take 2 things in that world and add all the corresponding places together, I get a sense of addition. And I hope you see that that is going to make an abelian group. It's going to have the same properties that you see on the screen right now, except now what I'm pointing at on the screen, the A and the B are not arrows anymore. The A and the B are now 3x5 matrices. And if you think this out, you'll see that the adding matrices is the same as the first 4 things here. They satisfy the same abstract properties. So it turns out that adding matrices of the same size, same number of rows and columns, turns out to be an abelian group. We're not thinking about arrows anymore. We're thinking about matrices now. If I would take a 3x5 matrix and multiply every object, every number in that 3x5 thing. Now, what's a 3x5 thing? It'd be 15 numbers. If I would take each of those 15 numbers and multiply it by 2, I would still have a 3x5 system in which everything is doubled. That turns out to be how we define scalar multiplication of matrices. When I put together the 2 operations of adding matrices and multiplying by scalars, I get a new world called a vector space. And what's in the book here describing the properties of vectors works where you interpret the heavy print A and the heavy print B, the boldface, as matrices instead of arrows. The point is that matrices of the same size are vector spaces. This is why I was trying to get you guys to learn the properties of a vector space, because we will need to use vector spaces for other reasons besides collections of arrows. Okay, so now what's in the book is only the arrows. But when you get to section 4 in the book, 3 being dot product, when you get to section 4 in the book author brings up, I hope you can see this on the screen, on the page now. The author brings up these strange looking things. Now, if I think of this, and there's a problem, in my opinion, with the book, but if I just think about this, what I see is 3 rows and 3 columns. I'm putting my finger on. I hope it's clear enough to see. If I don't think about those straight lines around it on both sides, the straight lines look like absolute value. Forget that for a minute. If I just think of the 9 things there, that's a 3x3 matrix or a 3x3 array, 3 rows and 3 columns. Notice there's no commas. There's just 9 things. Now, the way we write a matrix a lot of times is instead of those straight lines is we put big parentheses around them. So I'm going to get off the page here and try to write something that I hope is more readable, because I'm going to write big and I hope it comes out. If I take something, now I'm going to do a new thing here. Can you guys all see this? I'll make it bigger. Hope you can see this. I'm going to write the same letter here, but what I want to do is write subscripts. Now, That what I'm writing looks like 11, but it's not. I mean, it is, and it isn't. It is 11. We could argue all day as whether that's 11. Anyway, what you're supposed to, in a matrix, is supposed to be what's in the first row and first column. The subscripts are meant to be separated by what row and what column you're in. So this one is in the first row and second column. This one's in the first row and third column. That's what I mean by that. So how would we denote something in the second row and first column? Well, the A, what the A is nothing. It's just a notation. We would put 2, 1 here. Okay. And so hopefully, if I have a 3-row, 3-column thing, I would have it filled out. I haven't taken time to fill it all out, but I'd have 9 things here like the book did. Okay. Other times, sometimes people write square brackets instead of round brackets to tell you it's an array or a matrix. And we usually reserve the straight lines, like you saw in the book, to be something else called a determinant. So a determinant turns out to be a number that is associated with a matrix. Now think of it like having plots of land and associating with each plot of land an area. And somebody can say, I have 2 acres of land, and that's a number that's associated to the land. Well, determinants are going to be numbers we associate with arrays or matrices. And the way to describe a determinant sometimes, because these things differ, is to write straight lines around it. Now, because of the problem, because some people use straight lines to mean the matrix, and other people use straight lines to mean the determinant of the matrix, this can be confusing. So if I want to talk about the determinant of the matrix, whatever that is, it's a number, I put DET in front of it. Whereas the author in the text is going to, instead of having curved lines around it, is going to have straight lines. Everybody kind of understand? So when you see it in the book, it's not going to have DET in front of it. When I talk about it, I'm going to put DET in front of it because I know there are confusions between notations for how we describe a matrix and how we describe the determinant of a matrix. Now, is there anybody in the class that has never had determinants of a matrix? Or have you all had that somewhere? A little bit. I'm waiting to see if somebody will turn on their sound and tell me.
If I have, I can't remember.
Okay.
Yeah, me too.
All right. So maybe somebody talked about it, but you didn't learn it. And there's nothing wrong with it. I just need to know where to start here. Okay. So I will take it that you guys don't know much about determinants. So those of you who do, maybe you can teach the class or something. But, okay. Now, what you learn in high school sometimes, I mean, what I learned in high school is if, and I'm going to go up here, and if I have a thing with a 2x2 system, this is a 2x2 matrix. Now, when it's like 4 things, I might not do all this 1, 1, 1, 2, 1, 3 stuff because you can see the 4 numbers. I mean, so there's no reason to dude it up with which row and which column it's in because it's easy. If I were to do that, I'd be saying that A11 is the number A, A12 is a number B, and of course I have this is a 3x3 thing, this is a 2x2 thing. Anyway, what we do is to define the determinant of this matrix to be a certain number, and we compute that number by multiplying A times D, multiplying B times C, and subtracting. And this is what you may have learned about. Those of you who did learn about determinants, you may have learned this in high school. Then I learned in high school how to find the determinant of a 2x2 matrix. And so I'm going to write out the 9 things here now. I learned how to do a determinant of a 3x3 matrix. And that is another number. And now, this is not how we're going to learn it, but I'm interested to see if any of you did this. What we do in a 2x2 thing is we multiply these two things together, we multiply these two things together, and we subtract. Everybody does that way. So if you've had determinants of a 2x2 thing, I'm sure you did it that way. Any complaints, confusion with a 2x2, you all understand? Pretty easy. Whatever the numbers are, first, fourth, second, third. I say first, fourth because this is first, second, third, fourth in this world of 4 things. Okay, first times fourth minus second times third. Okay, how was I taught to find the number involved with a 3x3? Now I'm going to mess this up. This is how I was taught. Multiply these 3 numbers together and write it down. Multiply this one and these 2 together and write it down. That was this one. And multiply these 3 together. That's A12, A23, that's here, and A31, and add it in. Now, that's not the determinant, that's half of it. Then you multiply these 3 numbers together and write it down. That's A13, A22, and A31. And subtract that one. Multiply these 2 and this one together and subtract. That's A12, A21, and A33. And finally multiply this one and these 2 together. That's A11, A23, and A32. That's how I was taught. It made absolutely no sense. We had to memorize it. We did 10 problems and the teacher went to the next section. All right, nobody ever told me what it means or what you can do with it or why in the world we'd ever do something strange like that. But we did it. That's the way I learned it. Now, since that time, I've learned there's other things that people learn when you don't learn anything except how to do something without understanding why you're doing it. Other people learn other things you can do. There's other ways you can play with this to get the same answer. Anybody learn it like I did? Somebody wants to come in. Michael must have gotten thrown out some reason. Welcome back, Michael. Did anybody else learn what I just did? I'm just curious. I see one person. That a yes or a no? I saw one person shake their head. Most of you aren't showing me who you are. You're just showing me
No, I didn't learn it that way.
Didn't learn it that way, but you learned something.
Yeah.
All right. Let me ask you, Hannah, while you're talking there, not to embarrass you, but did you understand what in the world why you were doing it?
No.
Okay. Well, I didn't think so. I mean, I don't know. I mean, I don't know what they do. I didn't. I just learned how to do it, and I got A's on my test because I could do this. Now, the problem with this, if this is all we ever had to do with matrices, this wouldn't be too bad. And by the way, these matrices are called square. The reason they're called square is because the same number of rows and columns, so it looks like a square. This is a 2x2 square, this is a 3x3 square. We actually can play with different sizes of matrices, but for determinants, we need to have a square. Same number of rows as columns, okay? So we don't talk about the determinant of a vector, because a vector does not have a square matrix to make it up. Okay, what I want you to notice here, and there's no reason why anybody would know, but how would I do a 4x4 or a 5x5 or a 10x10? Well, you see how much more complicated what I was taught to find the determinant of this thing than the determinant of this thing. But there's no reason why you do all this nonsense to this one, whereas this one you don't do so much. But that's all I learned. Okay. So if I had to do a 4x4 determinant from what I learned in high school, I would have absolutely no idea how to do it. I might try to do some kind of game with rows and columns like I played here, but I don't know. If you look in the text in section 4 where the book talks about it, he only does 2x2 and 3x3, and therefore, in my opinion, misses the whole point of what in the world we're doing this for. Now, the author is developing this for one reason only, and that's to give you a way of computing cross products of vectors. But we teach a whole year, a whole semester in undergraduate called 511, where you learn about matrices. It takes a whole semester. In other words, matrices, dealing with matrices, or more properly, dealing with linear transformations. Turns out that linear transformations in math, every linear transformation has an associated matrix, and every matrix has an associated linear transformation. So when you study linear algebra, it's a whole branch of mathematics. We have people getting PhDs in it. Okay, so there's a lot more than talking about 2x2 and 3x3 determinants. But I want to teach you how you would find a 4x4 or a 10x10 or 1,000x1,000, whatever, determinant if you had to, because it turns out that they are very useful in solving problems that we have out in the world, but not just 2x2 and 3x3. So the book is going to stick to 2x2 and 3x3 because they can tell you a way to do it. And by the way, the book does not do it this way, give you a different way to do it. And that's fine. The way the book does it is great. And we're going to learn that too. But I want to teach you a little bit more about it because this is an honors class. And it's going to take us probably Friday also, because it's whatever, 18 after now to do it. But I want to try to just discuss this a little bit. What I want you guys to do when you read section 4 is learn how the author does it so that you can compute these things. And when you're doing it, you're computing what's called a cross product. Cross products are very useful. Anyway, but what I want you to see here is there's 3 of these that are plus and 3 of these that are minus. There's an equal number of plus and minus. In a 2x2 system, there's an equal number of plus and minus, namely 1 of each. If I have a 4x4 system and I figure out how to do it, it turns out I will have an equal number of positives and negatives, things that I'm going to play with. Now, the thing to look at here, and I'm running short of time here, but look at the second things that I have. I'm just picking some out here. Look at the second things in other words, look at the columns here. What you'll see in every one of these 6 things is 1, 2, 3, but not necessarily in the order 1, 2, 3. Here I have 3, 1, 2. Here I have 2, 1, 3. Over here I have 1, 3, 2. Here I have 3, 2, 1. Here I have 2, 3, 1. Now, so the 6 things I have here all involve different ways of turning 1, 2, 3 around. That's called a permutation. And some of you may have done that in high school. So if I have the numbers 1, 2, and 3, there are 6 ways I can play with them in different orders. I can have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, and 3, 1, 2. There's 6 ways. Okay. If I have 4 numbers, there are 24 ways that you can play with them. And it turns out when we do a 4x4 determinant, it won't have 6 things, it'll have 24. Now, the key here, which may hit you, is if I have a 2x2 matrix, it involves 2 things. That's 2 factorial. If I have a 3x3, it involves 6 things. That's 3 factorial. If I have a 4 by 4, it's going to involve 4 factorial things, namely 24. If I have a 5 by 5, there's going to be 120 things I have to write down. Now, I know we've gotten over time here, but the point is that half of them will be, I'm going to hang a plus on half of them and a minus on the other half. On a 4 by 4 matrix, when I take a determinant, 12 of them will be plus and 12 of them will be minus. When I do a 5 by 5, 60 of them will be plus and 60 of them will be minus. And that's because it turns out that there are what are called even permutations and odd permutations. And every system, no matter how big a system I have, consists of 2 kinds of ways of moving these things around. We'll talk about it Friday. And the idea here is to have one term where you pick one thing out from every row and column. And there are 6 different ways to pick one thing out of every row and column here. Half of them you put pluses on and half of them you put minuses on. And we will have a way to do that. That's easy to learn, but I'll have to explain it to you. So I want to talk about matrices a little bigger because we will have reason to do that later in math. But for section 4, we only need to worry about 3 by 3 and 2 by 2. So if you study that in high school, it might be time to dust off wherever you learned it and try to go back and look at it, or look in the book. The book sort of does a little bit of explanation of it in section 4, and we will talk more about it on Friday. But as of today, I am out of time. And so I hope that learning about this will be interesting to you. It involves permutations, it involves probability. There's all kinds of stuff that we can get into with this idea. We'll just touch it, but hopefully at the end of the day, not today, but the end of Friday, you will have a reason for doing all the stuff that you may have done in high school without knowing why. Okay, well, I'm done talking. I'm tired. I don't want to talk to you guys anymore. So I'm going to cut off the recording.